All right, let's get this show on the road before Kayla starts to take over. Hello, everyone. Hope you're well. Another great evening. It was actually a great day out earlier, but I couldn't go out. Hopefully you guys got to enjoy the sun a little bit. Let's actually just jump right into it. So boom, here's what we started last time. Let's actually finish up this section and we'll see where we can go from here. So last time, yesterday, we started covering improper integrals. Just a quick recap. Basically, these were integrals, definite integrals, they look like. However, they fail to uphold the assumptions for the fundamental theorem of calculus. Oh, yeah, so I had some issues uploading those. I think the video for yesterday should be up shortly. I just got around to uploading it today. So yeah, that was on my end. So it should be up. You should be able to see it pretty soon. So just to recap, we looked at yesterday integrals that they didn't quite obey the fundamental theorem of calculus. So remember when we were computing the integral from a to b of f of x dx from Calc 1, we had the fundamental theorem of calculus that told us how to compute this via antiderivatives. However, under the assumptions, the function was continuous. That's how we could apply the mean value theorem to get the evaluation theorem, as well as the length had to be finite, a finite length. That way we could actually do the Riemann sum thing. We could find the delta x and take a finite length, slice it up into meaningful chunks. Now, whenever an integral does not obey one of these two, we call that an improper integral. And there are basically three ways in which this can happen, where any and all of these three, if any one of these occur, you have an improper integrals, but potentially all three can occur, or any two or any one. Once any one of these three things occur, it means that one of these two assumptions are not fulfilled. So either your function is discontinuous at finitely many points. So there's a situation where a function can be discontinuous at infinitely many points, but those sort of functions are above our pay grade. That's sort of functions that only math majors have to worry about. Then we have the lower limit can be negative infinity and or the upper limit can be positive infinity. Now here's the thing. These situations, the points that made our function discontinuous, as well as if our input went to negative infinity or positive infinity, we call those bad points, not an official term. And to compute improper integrals, what we did was we identified the bad points. We broke up the integral using this property to expose the bad points such that only one bad point is exposed per integral. We use limits to approach the bad points. We can only approach a limit from one at a time. That's why we only need one bad point per integral. Then we compute the integral as the fundamental theorem of calculus tells us, and we take the limits afterwards. If the limit gives us a finite real number as the answer, we say that is meaningful in some sense, and we call that convergent. So we can have an improper integral converging. Otherwise, if the limit does not exist or goes off to infinity or negative infinity, we say the improper integral diverges. So we did some examples of breaking guys up like that and actually doing them. Let's look at one of the complete examples. We also spoke about Gabriel's horn, which was a crazy paradox, which now that I'm thinking about it, and I have to check the video which just is posted. I think I said this in the opposite. I think I said it had finite volume and infinite area, but it's actually the other way around. It has finite. No, I said that what I just said was the right way. I think in the lecture I said the opposite. If I did, I'll put a comment on that. Okay, so the idea is whenever you have bad points, here we have two of them. You break up the integrals so that you only have one bad point per integral. This will allow us to approach with limits. So in this situation, I broke it up so that 0, which is a bad point, is on one of the integrals, and the infinity, which is another bad point, is on the other integral. We use limits to approach these. Use a different limit for each one, and then you compute what these guys would be, and you take the limits. We also learned that if any one limit messes up, then the whole thing messes up. So you only need to care about the guys that are divergent, if anything. They all need to converge, And when they all the limits that you had to break it up into, if they all converge, you add up the answers together. That is the number that the overall integral converges to. If any one of the limits mess up, then the integral diverges. Okay, so I think that's pretty much all the new things we learned. We applied what we learned to derive a very important theorem. That is a theorem about this kind of integral here. The integral 1 to infinity of 1 over x to the p, which is actually a remarkably useful improper integral. And it turns out that we derived by a theorem that such an integral will only converge if your p is greater than 1 specifically, and it will diverge every time your p is less than or equal to 1. And we actually went through and we actually derived that, and that's where we started. Now, this theorem, it's useful for many reasons, as I mentioned. For us, why it's going to be important is because it's going to be a guy that we're going to often use in comparison theorems. Okay, so what are comparison theorems and why are they even necessary? Okay, and so now we're into new material. We didn't talk about this yesterday, so I'm going to talk about this now. Okay, there are times when you have improper integrals when the method that I described earlier will not work. Because notice, for the method that we described earlier to work, ultimately at some point, you should be able to actually calculate the integral, right? So you use limits to replace the bad points, but ultimately we are going to find antiderivatives and all that good stuff and then take the limit at the end. However, sometimes we have an improper integral where the actual function, we don't know how to actually take the antiderivative. Maybe it's a rule that we just don't know about, or it's a function where we know for sure that there is no antiderivative in terms of our familiar functions. So that is the situation that the comparison theorems help us to handle. So here we have an improper integral, but even if I went through and I replaced the bad points and all that, I still end up with an integral that I don't know how to actually compute. So what we do instead is we actually compare them to an integral that we do know how to compute. And this leads us to the comparison theorems. Now we'll cover two of them. We'll cover what's called the direct comparison theorem, or just comparison theorem. Normally when someone says comparison theorem, this is the one they're talking about. But for emphasis, you can call it the direct comparison theorem. There's going to be another comparison theorem called the limit comparison theorem, which we normally actually say the word limit as a part of the name. So here is how the comparison theorem works. It's based on inequalities, right? So suppose we have two functions that are continuous, f and g. They're continuous on some interval where at least one of it has a fixed interval, right? So a to infinity. And I know that my f of x is always less than or equal to g of x on that interval. And they're both positive. So they don't oscillate across they don't cross the x-axis at any point. They're always greater than or equal to 0. Now, you learned in Calc 1 that integrals actually obey inequalities. So if I know that f is less than g, then it means that I can take the integral of this and the integral of that, and the integral is not going to mess with the inequality signs. Integrals obey inequalities. So now we have this part here, which tells us that the integrals are also going to obey that inequality. Both integrals will be greater than 0 at the same time, and the integral of g is going to be larger than the integral of f. Now, here is the important part. Here is the conclusion that we can make. And then I'm going to show you how we'd apply this. Okay? So basically, if the larger integral converges in this scenario, then the smaller integral is forced to converge. Okay? So if the bigger one converges, meaning the bigger one stops at a finite value, then what you would have is that the integral in the middle is going to be between 0 and some finite value. And it will have to stop at some point. It has to either stop at the value before the upper bound, or it has to stop at the upper bound itself. It cannot go off to infinity, right? It also can't go off to negative infinity because they're both positive. However, because these are positive functions, the area under the curve is going to be non-negative. And so what's going to happen is we are accumulating area in general, as long as it's above the x-axis. And so the area is growing in some sense. And so the idea, it says here, the growth has to stop at some point. because there is an upper bound. It cannot grow past some upper bound, which is set by the g. So if the larger one converges, then the smaller one is forced to converge. So what this can basically tell us is maybe f is an integral that I care about and it's an improper integral, but I don't really know about how it converges or not. I can't really calculate it. I don't know how to actually find the antiderivative. The idea is if I can find something that's larger than f, where I can actually compute it, I can compute antiderivatives and I can find the answer, I can use whatever answer this one gives me to determine that this one must have an answer. And I can know that the answer is going to be within this region here. Conversely, if the smaller integral diverges, then it's going to force the bigger one to diverge. Okay, so here, notice in this scenario, our integrals are always positive, right? Which means if your f diverges, it's going to diverge off to infinity. So here, if this guy goes off to infinity, what's going to happen to the guy on the right? Well, he also has to go off to infinity because he always has to be bigger than or equal to the guy in the middle. So it turns out, once you have two functions f and g such that 0 is less than or equal to f is less than or equal to g, these guys are continuous, then the improper integrals from a to infinity of these functions will obey the same inequalities, and if the larger integral converges, then the smaller one will converge, and if the smaller integral converges, then if the smaller integral diverges, then the larger one will diverge. And it turns out, and this is actually very important, let me actually color this one and I'll leave it colored. You cannot make any conclusions in any other case. That is often something that students forget. What do I mean? What if the smaller one converges? So in other words, this is saying if the integral of f converges, this tells us nothing about g. So knowing that f converges, then we are still left to guess what's going to go off with g. And if the integral of g diverges, this tells us nothing about f. Okay. And we can take a quick second to think about why that must be true. Let's say the smaller one converges. Then whether or not the upper integral diverges or converges, you'd be none the wiser. G could go off to infinity and the inequality would still hold. G could also stop at some number bigger than f and the inequality would still hold. The inequality is going to hold in either case. I don't know which one I'm actually in. What situation am I actually in? Similarly, if your upper one diverges, go off to infinity, then your lower integral could either go off to infinity as well, or it can stop at some number before that, and it will still be less than or equal to infinity. So there's no way for you to actually tell the difference, right? However, in these first two situations, you can definitely tell the difference. If the upper one converges, the smaller one must converge, and if the smaller one diverges, then the upper one must diverge. This is called a direct comparison test. Okay. Any questions on that idea? Before we move on. So I've been rambling for a while. I want to make sure that we all kind of get what I'm saying. We're good? Yes, okay. All right. So essentially, I want you to recognize what we actually did here. We are using the fact that we know about one improper integral to determine what's going to happen to another integral. Now, I can't determine exactly what the value of this other integral is going to be, but I know it's actually going to give me a finite value or it's not going to give me a finite value. And so what we actually did is we kind of pull a Thanos with the improper integrals, and we kind of used an improper integral to destroy another improper integral, right? So here's an improper integral that I care about. I don't know how to actually compute this, but hey, I know about this other improper integral. So I'm going to use this improper integral to tell me about that improper integral, right? And this is something that we usually when we do this is called a comparison theorem. You have different comparison theorems in other contexts. Yes, the dad jokes. I have to thy own self be true. Okay, right? Now, there's another situation. Notice here that you actually need to know the inequality relationship between f and g to actually make these conclusions. You have to know that the g is larger than the f, or the f is smaller than the g. And you have to know specifically what happens to the upper one in a certain scenario versus what happens to the lower one in a certain scenario. It turns out that there are scenarios in which we are not going to really know this information. However, there is still something that we can do. There's a second comparison theorem, and this one is called the limit comparison theorem. This one has this assumption here. Suppose f and g are continuous on this, and no other assumption is made. We don't know who is bigger than who, and for this theorem, we don't actually care. What we would do, though, is we take the ratio f divided by g or g divided by f, and assuming that we're not dividing by 0 at any point, we'll actually find that limit. And if the limit is a positive real number, and only if the limit is a positive real number, it doesn't really work. It does not work in any other situation. L is a positive real number. So you take the ratio, you take this limit, and if L is a positive real number, then what's going to happen is that the integral of f and the integral of g will do the same thing. They'll both converge, or they'll both diverge. So here's something that's going to be useful for us. This is going to tie together the theorem that I mentioned at the end of last class and the theorem that the theorems that I'm just mentioning now. It turns out that the other integral that we're going to use to talk about the one that we actually care about is very often of the form 1 over x to the p. We can very often actually manipulate it to look like that form. And because we know about what happens to 1 over x to the p very well, we can actually figure out what happens to a lot of other guys as well. And so that's how the theorem, the 1 over x to the p theorem, is used with these guys. So if I have some function and I can find a 1 over x to the p integral that I know converges, that's larger, it tells me that the smaller one will converge. If I have a sum integral and I can find a 1 over x to the p integral that diverges and is smaller, I'd be able to determine that the upper integral diverges, right? So this sort of integral here actually comes in handy a lot when it comes to this. Now, one other thing I do want to mention, all those, did I mention here? No. You have to remember back in Calc 1 when you were doing limits, the skills that you had when you were doing limits, especially when you're applying things like the squeeze theorem, you are going to want to do those skills here. Because usually, when you have one improper integral and you want to actually talk about that integral, you have to find some other improper integral to talk about it. You want to know that you're constructing that integral in some predictable way. You want to be able to tweak the integral that you currently have to look like something else that you actually know about. And of course, many times you're going to want to tweak it in such a way that you know you're getting something bigger or smaller. And so that's going to be important. That kind of skill set you actually developed back in Calc 1. So hopefully you guys remember all of that. Let's actually jump into it. So I actually explained everything you need to know about these theorems. So maybe you can like take a screenshot of this because we're going to be using these in the examples later on. So I'll give you 5 seconds to screenshot that. 5, 4, 3, 2, 1. Okay. Screenshot this one as well. It's a limit comparison theorem. 5, 4, 3, 2, 1. Okay. All right. So now you have those two theorems. And if you haven't already, you should screenshot that one, or you should just remember that one. The integral from 1 to infinity of 1 over x to the p dx converges only if your p is greater than 1. It diverges in all those situations. Okay, that being said, let's actually jump into the examples. So we have 5 examples to wrap up this section. Let's get down to the nitty-gritty. Okay, so here's an integral. Okay, good. You know, if you have Windows, you hold on Shift, the Windows button, and S, it puts you in a screenshot mode right away. And if you have Windows 10, you'll see a little pop-up notification thing that asks you if you want to save the picture or not, but you cannot actually copy it right away. Anyway, let's look at this integral here. Integral from 0 to infinity of x over x cubed plus 1. We are going to determine whether or not this integral converges or diverges. Now, the first thing I want you to appreciate is that actually, we probably could integrate this one, but I don't think you would want to. So you might recall that x cubed plus 1 is actually the sum of cubes, so you can actually factor that into this. And then you might be able to do a partial fractions. That's going to be very annoying though, and I'm not exactly sure if that's going to actually get you anywhere nice. But yeah, so this one isn't so bad, but hey, we're easing ourselves into it, all right? So ultimately, I want to be able to determine whether or not this converges without actually having to compute an integral. So we are going to use the theorems that I just mentioned, the 3 theorems that the 2 I mentioned today and the one I mentioned from yesterday. So any ideas on what we can do here?
I guess you can separate the integral, and after you separate the integral, you can integrate it and plug in the endpoints.
Separate how?
Separate the integrals. Like, I'll recommend that you should put x over x cubed subtract x over positive 1, and after that you integrate it. Like,
Oh, you can't actually do that. You can't split a fraction across the denominator. Yeah, you can't actually do that. If you have a over b plus c, it's not the same as a over b plus a over c. That's not true. Right. Infinity is the only bad point here, so we don't really need to break up the integral any further. Okay, so if the car is about, well, what if we use the limit comparison? Well, you tell me, how would you actually apply the limit comparison? What would you compare it to? One over x cubed. Why would you do 1 over x cubed? One over x cubed is actually not going to give you what you want, right? Like if I said, like if I call this f and I call g 1 over x cubed, what's going to happen if I take like f divided by g, right? And take the limit. That's going to give me the limit of, there's going to be an x to the 4th plus dot 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 up here. And then in the denominator, I'm going to have an x cubed. Da, da, da. That's going to go off to infinity. So 1 over x cubed plus 1 is not who we want to compare this to. Even if we're doing the limit comparison theorem, that's not actually going to be very useful for us. Remember your training grasshoppers. Remember back in Calc 1, when you wanted to do this like a squeeze theorem or something, how did you actually make something comparable? Something maybe slightly bigger or slightly smaller? right? The thing is with 1 over x cubed plus 1, it is sometimes bigger than x over x cubed plus 1, but it's sometimes smaller, right? If your x is less than 1, then the original is smaller, but if your x is larger than 1, then the original is bigger. So you pick something now that actually changes. Okay, so now 1 over x cubed is probably a better guess. However, you'd still run into the same problem. If we divide them, if you're doing the limit comparison, you'd still get x to the 4th over nx cubed, and that's going to go up to infinity. Also, again, not sure who's bigger there. How do you know that 1 over x cubed is big? If I want to use direct comparison, I wouldn't know. Okay, so let's go back to principles. Let's go back to the basics. I have a fraction. How can I get something that's slightly bigger or slightly smaller? Like in general, give me a general principle here. How can you make a fraction bigger or smaller? What are your options? Just as a general principle. Simplifying won't make something bigger or smaller, right? Simplifying is just, you're just rewriting it in a different form. You don't actually change the value. At least if you simplify it correctly, you shouldn't change the value of the thing you're simplifying. No, factor would be what you would do to simplify. Okay, so here's the thing. Here's how we can make a fraction bigger or smaller. If you make the denominator larger, the fraction will get smaller, right? And if you make the numerator larger, the fraction would get larger, right? So think of fractions. If you have like 1 over 10 versus 1 over 100 versus 1 over 1,000, right? So this was something that you guys saw back in calc, at least I hope you did, right? And just look at what the function y equals 1 over x looks like, right? It gets smaller as your x gets larger, right? So this is something that we knew for a while, right? Right, grasshoppers, we knew this. If you make the denominator of a fraction larger, then the overall fraction will become smaller. If you make the denominator smaller, the overall fraction will become larger. So in fact, here's something that I can mention here. I think I deleted someone I didn't want to delete. Here's something, note. Let's say I had x over x cubed plus 1, and I did something like, you know what? Let's get rid of the 1 in the denominator. Now, when I do that, right? What did I actually accomplish here? Is the new guy bigger or smaller? The new guy's bigger because the denominator is smaller, right? I know for sure this is bigger. There is no doubt. There is no question, right? I made a change where I know for sure I got something bigger, right? Now, this thing here that's bigger is that. And that looks like a 1 over x to the p. And I know everything about 1 over x to the p. Now, there is a small issue here. Does anyone see what the issue is? Like how using the 1 over x to the p thing here is not really going to help. Or there's an issue with using. The idea is if I integrate this, it's going to be less than or equal to the integral of that. The bounds, right? You guys took a screenshot, right? So you know that in the theorem, we need 1 down here. Of course, it can work with any positive number, but specifically in the theorem, there's a 1 down here, which means the fact that there's a 0 down at the bottom in the original, that's a problem. I can talk about this one, but what would happen so knowing that I can only talk about the bounds from 1 to infinity, How do I make a conclusion about the bounds from 0 to infinity? Ideas? Now, there was some that we did last class that you should be able to actually put together. So here's I. Right. Got it. You can break it up. You can break up I into the integral from 0 to 1 plus the integral from 1 to infinity. Now, what do we know about that? This is less than or equal to this guy plus that guy, because I made the denominator smaller. Denominator smaller, so we get a larger fraction. And this guy converges by theorem that we mentioned before, because here your P is actually equal to 2, which is bigger than 1. This guy is just going to be some finite number. It's the area between 0 and 1 of this thing. It's going to give you some finite number, which means I converges by, you can say comparison or direct comparison. And you could even include comparison with what if you want, but just saying that that converges by comparison is usually good enough. You can say comparison with, if you want, the integral from 1 to infinity of 1 over x squared dx. Okay, so this is a way in which I can use a comparison theorem. Notice here, I just determined that this integral converges. It has a meaningful answer, and I didn't actually do the integration to figure that out, right? I just know about some other integral, and I use the fact that I know about that other integral to tell me about the original integral. So this is the power of the comparison theorem. Now, of course, there might be a situation in which I would want to know what the value of the original integral is. But the comparison theorem would help you in a situation where it's like, well, you're not sure whether it converges or not. So you're not even sure whether or not you should spend the time trying to figure out if there's an answer. The comparison theorem will tell you, hey, there's an answer. So now you know, oh, there is actually something worth looking for. This integral might be important to me in some context, and it's an answer that is meaningful. It's worth actually searching for. Now, how do you actually go about searching for an answer to the integral? Well, that's kind of what the next section is about. But for now, you just know there is some meaningful answer to this integral. There is a finite area under the graph of y equals x over x cubed plus 1. And I can compare it with the P series to actually determine that. So there you go. That being said, this one isn't an impossible integral for a Calc 2 student. You could, if you remember the sum of cubes formula, just break it up with partial fractions, and you'll probably end up with a very ugly trig sub at the end of the day. But it's doable. Yeah, you'll end up with a part of a log and then a part with trig sub, or just rewrite it so you can use the arctangent. Okay, here's another one. Now with this one, we aren't so lucky. You see, this guy doesn't have an antiderivative. So if you're thinking of some clever trick to actually integrate this one, you're going to be out of luck. So ideas. And again, remember your training from Calc 1 grasshoppers. So remember, think back to like squeeze theorem and all that stuff when you were doing the limits where you were trying to get upper bounds and lower bounds. There is a certain thing that you always kind of think about whenever you see a trig function. Besides the special trig limits, there's something else. So you see something like this. What are you thinking? Ideas? You guys remember that there was a special trig limit? Okay, so let's actually kind of try. Let's see if we can lead ourselves into it. You remember there was a special trig limit that looks like this, right? That was equal to what? 1, right? Now there's a limit that looks very close to that, right? So someone can say here infinity, and of course the students who aren't paying attention might say that's 1, but of course the students will recognize no, it's only 1 if there's a 0 here. If there was an infinity, what was the actual answer? Wait, no, look at this one. This is actually 0. There are a couple ways you can know about that. Another thing that you learned about limits was how functions behave. And you knew that the polynomial is going to outgrow the trig function by a lot. And so in Calc 1, what sometimes you would have been asked is to prove it. Prove that this is 0. How would you actually show that that was 0? Do you remember what you actually did? If you use the squeeze theorem, do you guys remember what you did to actually accomplish that, to show someone that, yeah, this is actually 0? Well, that's not using the squeeze theorem. That's using what a limit is. You plug in numbers closer and closer. But the thing is, here we're going to infinity. What is a number close to infinity? There is no such number, right? The plug-in strategy doesn't work for infinite limits, or limits at infinity, rather. You had to prove that this was 0 with the squeeze theorem. Do you remember what you guys did? Okay, let me remind you. Here's what you did. You don't remember, even though you were there. Okay, here's what you did. You started out by focusing on the sine. And you noticed something about the sine function. You noticed that it had boundaries, right? The sine doesn't just go all over the place. It is predictable in somehow. Meaning, you do know boundaries for sine. What are they? Right, -1 and 1. And then what you did was you divided everybody by theta. So you started out with a trig function, you bounded the trig function, and then you build up to the original function from the trig function. Then you took the limits of everybody. What you'll realize here is that the outer limits went to something that you knew how to deal with. Those both go to 0 for obvious reasons, because that's just the limit as theta goes to infinity of 1 over theta. It's just like the limit as x goes to infinity of 1 over x. And what you get now is that you have this limit stuck in here. And so you could actually conclude, because this limit is squeezed between 0 and 0, the limit of sine theta over theta as theta goes to infinity is 0, right? So that's how you prove with the squeeze theorem. Okay, so that's what you did. We started out by taking control of the trig function. You bounded the trig function, you built everything else around it, right? That allowed you to talk about a limit very efficiently. Okay, so we're going to do the same idea, but with an integral. Now that I showed you guys that, I reminded you of that. Can you see what you would do here? suggestions? Here I have another trig function in play. There's a cosine squared. What can you tell me about that, and what can you infer from that? I'm not sure what trig identity you're using. I mean, in the thing I just showed you, did I actually use a trig identity? I didn't use a trig identity just now. Scroll up where? Oh, I actually erased it. Okay. Here. So you wanted to prove that this was 0 by the squeeze theorem. You start out with the trig function. You find boundaries. You build up to the other function that you care about. You take limits of both sides, limits of all sides. Realize that it's bounded between 0 and 0, and you can make a conclusion from the squeeze theorem. So this is not exactly how you're going to do it, but it's something worth comparing to. Okay, so look at that. And now think of this guy. Ideas? Anyone connecting the dots? Set up an inequality. What inequality? What inequality? How? Specifically how? Sure, cosine squared is greater than or equal to 1, minus 1, and less than or equal to 1, but the lower limit there isn't great. We don't need the minus 1. You can use 0 and 1 because it's a square. And of course, why would you opt for the 0 and 1? Well, you see, I have this theorem that we had earlier that has this 0 right here on the lower bound, right? So while it's true to say cosine squared is between minus 1 and 1, Jason, you got to stay on topic here. We're actually dealing with an integral right now. So
Oh, sorry
pay
about
attention.
that. I mean, like, basically, like, trying to, like, oh, my bad.
Yeah. So here, you start out with an inequality. Realize that cosine squared is going to be less than or equal to 1, but greater than or equal to 0. I can divide all sides by 1 plus x squared. 1 plus x squared is positive, so it doesn't turn the inequalities around. And now I can talk about the integrals of each. Now I throw in the integral that I actually care about, the integral from 0 to infinity. Notice what this is saying. Well, the one on the lower bound is going to be 0. The one here is going to be 0 to infinity of cosine squared x over 1 plus x squared, the guy that I care about, but I don't know how to even do that. And the upper bound is this one. So now we have that, which might remind you of the direct comparison theorem. Do you see how to continue? What can you say about the bigger guy? What can you say about the guy here? Integral from 0 to infinity of 1 over 1 plus x squared. How would you deal with that? It's arctan, right? So this is why we have memorized those formulas, right? That guy is going to give you tan inverse of x between 0 and infinity. And technically, yes, you have to buy the limit as n approaches infinity.
You would get pi over 2 as your answer.
What you're going to get is you would get pi over 2 as the answer. So this guy, the upper limit, converges.
That's what I just said just now, pi over 2 as the answer, because, you know, if you were to plug in, like, you know, infinity, the tan inverse of infinity, you would get, you know, sine 90 over cosine 90, which would be like, you know, pi over 2.
Yes. So now you had another option. You could actually compare this in turn to the integral of 1 over 1 plus x squared and do a little trick like we did earlier, but that's just more far removed from the answer. This integral is actually pretty easy for us to deal with, assuming we remembered the formulas. So now we can immediately say I converges by comparison. Now, at the moment, I don't know what it converges to. I just know that it converges. I know it adds up to some finite number. There's a finite area from 0 to infinity under this guy, where this guy I'm calling I. This is why we need to remember our training, grasshoppers. Now, this isn't true forever, but this is going to be true for a while, right? You're going to realize that harder problems are really just a bunch of smaller problems, right? If there is some kind of a thing that you don't fully understand, you have to break it down back to the simpler times, right? Go back and say, when have I been in a situation similar to this? What did I do, right? These are the kind of things you want to remember. Your big problems are just a bunch of smaller little problems. A lot of times students they misidentify that. You guys shouldn't be like that. You guys, I'm telling you the truth now, you're gonna pay attention, you're gonna learn from this, okay? So a lot of students, there are a lot of students who might tell you, oh, calculus 1 and calculus 2 is hard. And really their problem is algebra, or it's something else. It's something else that's before that, right? Whatever problems you're having, your problem actually occurred before the thing that you're currently working on. So be aware of that. So these are just some things that you have to keep in mind. Remember, how did I deal with trig functions? If I have something to get an inequality, how did I get an inequality before? How did we deal with situations like this in Calc 1? When you're in Calc 2, it doesn't mean you forget all your Calc 1. So yeah, this one we can say it's a comparison. We all need to review limits. Yeah, so we all need to review our limits. We need to remember all these little tricks that we used to have. We need to remember all the simple little things like, oh, I can just, if I make the denominator bigger, the fraction gets smaller. These little simple things like that is what's going to make the difference. Once you have all those little nuggets of knowledge at the forefront of your mind, which hopefully under normal circumstances, this is what a quiz is meant to do. This is why I normally test students on the rules, right? When you know the rules so well, and they're always like on the tip of your tongue, you'll see how to apply them in the strangest situations. You'd be in a situation and you'd be like, oh, this is similar to this other rule I know, or this is similar to this pattern that I'm familiar with. And you just kind of build on that, and you build on that, right? And that's going to be true for a while. I mean, we're still in undergraduate mathematics here, right? Everything that you're ever going to see in undergrad is just built on something from before. When you go off into math research, that's when you have to come up with something actually new, something that the world has never seen before. For now, all your hard problems are just a bunch of smaller, easier problems. You need to think of how to dissect it, think of what the lessons you've learned, remember your training, and you just piece things together. So that's that guy. Here's another one with a trig function. And yeah, and normally how you want to think of methods. So when I give you a method, like when I told you about, here's the strategy for how you approach integrals. Really, the strategy is just a way for you to identify what is the simpler thing that I'm not seeing, right? When you do a substitution, it's not like it's magic. The only thing the substitution does is it rewrites the integral that looked complicated before. It rewrites it in a simpler situation. It rewrites it in a simpler form that you already know how to deal with. And the method that I'm giving you guys are, oh, first check this, then check that, then check that. It's just a way for you to identify what are the simpler steps that you can take to break the integral down. All right, here's another one. All right, go. With all the lessons we've learned so far, try to get through this one. What do we do here? Integral from 1 to infinity of 1 plus sine squared x all over the square root of x. You don't have to integrate this exactly because we can't. Tell me, does it converge? Does it diverge? How would you figure that out? Direct comparison? All right, tell me how you would make the comparison. Okay, you guys are being too vague. Get specific with me. Like, how do you do this? So the smaller one is 1 over square root of x. Okay, so you're going to start, remember how we started? We started with nothing but the trig function. We know that that is between 0 and 1. And we build things up, which means we can add 1 to all sides. And then we can divide all sides by a radical x. So I started with a trig function, and then I built up to the more complicated function. Again, it's a strategy that I've seen before. I know how to deal with this now. I see a trig function. This is one of the go-to strategies. Kind of build up around it, because whenever you're dealing with a sine and cosine, you know how to bound those very well. At this point, we can go through and we can take integrals. Okay, so based on that, so we're going to take the integral from 1 to infinity. We're going to take the integral from 1 to infinity. We're going to take the integral from 1 to infinity. All right, so give me a conclusion. Tell me how you know it's true. And of course, these are all greater than 0, right? Because my x is 1 or larger, so 1 over the square root of x. It will diverge. How do you know? What are you looking at to tell that it's divergent? Okay, good. That's what I wanted to hear. You're looking at the smaller one, right? You do not want to look at the upper integral in this case, because the upper one actually doesn't matter, right? what you're focusing your attention on is the two guys here. This guy is now irrelevant. Why is he irrelevant? Well, he diverges and he's the upper integral. If the upper integral diverges, remember we had that theorem. In all other situations, it's not useful. He's the upper integral and he diverges, which means you cannot make any conclusion based on the 2 over radical x guy. You have to look at the smaller guys. Now, when you look at the smaller guy, this guy is 1 to infinity of 1 over x to the 1/2. Now, this guy diverges. Since your p is equal to 1/2, which is less than 1. So the smaller integral diverges, which causes this one to also diverge. And so that is your conclusion here. I diverges by direct comparison. Or again, just calling this guy I because I don't want to rewrite it. Are we getting it? How are we feeling? Want another one? It's too easy with the signs. Let's do some secants. All right, go. Ideas. What do you know about secants? How are you going to use that to your advantage? Maybe let's think about secants. How does a secant behave? Can you bound a secant? How do you bound a secant? What's the boundary for a secant? Anyone? Bueller? It's not between -1 and 1. Don't forget what secant is. Secant is a 1 over cosine. Right? So we're here. Boom, boom. What does the cosine look like? This is let's look at the cosine. So this is y equals cosine. Now your secant is actually 1 divided by cosine, which means whenever your cosine is 1, your secant is 1 as well. And whenever your cosine is -1, your secant is -1 as well. Now, what happens in the interim? Well, as your cosine is going down to 0, you're taking 1 dividing by 0. So what happens is there are asymptotes here. There are asymptotes wherever the cosine hits 0. Right? Now, as I inch closer and closer to 0, what actually happens? Well, you're going to shoot up to infinity, right? So this guy is going to shoot up that way. This guy is going to shoot up that way. That should not go up. Right, that's going to shoot up that way. So notice that your secant is always greater than or equal to 1 or less than or equal to -1, which means your secant squared, if you look at that guy, your secant squared is always going to be greater than 1, strictly speaking. Secant squared is always going to be bigger than 1 because your secant is always going to be a value that's larger than or equal to 1 in absolute value. So that is what we have. So now what you notice is that if I look at this guy, that is going to be bigger than this guy. And what we can do is we can focus on this guy. Now, that guy for sure, as long as you're not at, of course, you can't be at 0, you don't know what's going on at 0, but for sure, for x not equal to 0, this is definitely bigger than 0. Right? At all points except 0, it's going to be bigger than 0. So let's focus on just this guy right here. This would be like the limit as n approaches 0 from the right of n up to 1 of 1 over, this is x to the 1 plus x to the half, that's x to the 3 halves. That's x to the minus 3 over 2. You add 1 to the power, you get minus 1 over 2, divide by the new power. Limit as n is approaching 0. What you're going to notice is that if I plug in 0 into the x to the minus blah, 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 this guy diverges. Of course, he's going to diverge off to infinity. This thing is blowing up. So this guy here is going to diverge by direct comparison. And so we have that. So that's that one. Last example here. So all these we figured out using direct comparison. This one is actually a nice one for the other method, believe it or not. So here's another thing that we learned about limits, just to remember our training. Whenever we're taking a limit approaching infinity and we had a ratio of polynomials, what did we concern ourselves with? Well, do you remember? Like in this case, I have a cubic polynomial. I'm divided by a 5th degree polynomial, a quintic. I'm looking at an integral where the limit is going off to infinity. What converges to 1? What do we think about? So going back to Calc 1, what did we think about? Partial fractions wasn't done in Calc 1. And how would you do partial fractions here? You'd have to be able to factor the denominator. Can you think of a way to factor x to the 5th plus 2x plus 1?
You would probably have to use like basic integration, like, you know, the basic integration rules. That's what I'm assuming.
What basic integration rules?
Basic integration rules, like, divide, like, by each of them. Let's say like x cubed over x to the fifth would be like, 1 over x squared, which is 1 x to the negative square. That's what, like, for example, like that.
And what about the other parts? Because this doesn't really factor, I don't think. I think I picked an example that the denominator doesn't really factor. Right. What Samia said. That's going back to basic principles. You're going off to infinity, you focus on the highest powers. That's what you do, right? And there was a reason why you did that. You could, the algebra trick would be to divide the top and bottom by the highest power of x. So you go through and you divide by x to the fifth in each individual term. So x cubed over x to the fifth plus x over x to the fifth plus 10 over x to the fifth. And in the denominator, you have x to the fifth over x to the fifth plus 2x over x to the fifth plus 1 over x to the fifth. And then you can basically determine that you can determine what these guys are going to do close to infinity based on where the highest powers are. So you kind of had this idea that you just, and I mean, maybe I should actually copy this so that you can see, because I'm going to mark this guy up. So you learned back in Calc 1, you're going off to infinity, only the highest powers matter. You can essentially ignore everyone else, not for a direct calculation, but in terms of the behavior. What is it going to behave like? So you will notice that this guy is going to behave like, he's going to behave as if once you're going off to infinity, he's going to behave like that guy. Now, I cannot always do this. I just want to emphasize that. I can't always do this. I'm allowed to make this kind of leap in logic because of the infinity sign, right? Because I know my x's are getting huge. I know that once x gets really huge, it's not going to be for a while. Bigger than a billion, bigger than a bajillion, bigger than whatever, right? But when they're getting huge, I can only focus on the other ones. Now this, I can only focus on the highest power. I can choose to only focus on the highest power. This is another lesson that we learned from limits in Calc 1 that we can use to our advantage. Here, notice that this guy behaves like that, which converges by theorem. Now here's the thing though. How am I going to make the comparison? I just ignored all the little guys. Do I know that I got something bigger or smaller? Well, in this situation, I submit to you that it's kind of hard to tell. Notice that by taking away the denominator, the 2x plus 1 from the denominator, I've made the denominator smaller, which means that the overall fraction is going to be bigger. However, at the same time, I subtracted an x plus 1 from the numerator. So I've made the overall fraction smaller. So notice that to ignore everyone except the highest powers, I put myself in a situation where I both made the fraction bigger and smaller at the same time. Now you're in a situation where I'm not sure who wins. Did I make it more bigger than I made it smaller so that the overall thing is bigger? Or did I make it more smaller than I made it bigger so that the overall thing is smaller? Like it's hard for you to tell. It's hard to tell if this guy, it's hard to tell if this is larger or smaller than the original. So this means whenever you're in that situation, do not use the direct comparison test. remember the direct comparison test, we need to know who is bigger and who is smaller, and depending on who converges in that scenario or who diverges, I can make a conclusion about the other guy. Here, I can compare this reasonably to something else. I just don't know how, if that thing is bigger or smaller. So what I do instead, let's do limit comparison. So if I look at my f of x as, let's say the original guy, this guy. And let's say my g of x is the other guy I want to compare to, the 1 over x squared. What I would look at now is that the limit as x approaches infinity of, say, f of x divided by g of x, that is going to give me the limit as x approaches infinity of x to the 5th plus x cubed plus 10x squared divided by x to the 5th plus 2x plus 1. And what is that limit? Talk about Calc 1. It's 1, right. So when the highest power is the same in the top and bottom, the limit at infinity goes to the ratio of leading coefficients. If the highest power is in the denominator, it will go to 0. If the highest power is in the numerator, it's going to go to plus or minus infinity. You have to watch the signs. What's nice about 1 is that 1 is actually greater than 0, which means this is a positive real number. Why is it important that that's a positive real number? Well, in the limit comparison theorem, we are told that if we took the limit of the ratio and we got L, where L is a positive real number, we can make a conclusion. Both integrals will converge or both will diverge. They will both do the same thing. In this scenario, I know that this one converges because it is one of the theorem where the P is 2. And so both will converge. I converges by limit comparison. Where's this guy? Where this guy's my eye. Okay, so sometimes you're doing your little algebra mumbo jumbo, you're finagling things, you're reconstructing things, but you do it in such a way that you're not sure who's bigger or smaller, or you didn't have a trig function that you bounded between inequalities, so you really don't know who's greater than or equal to who. Whenever you're in that situation, that's when you apply the limit comparison theorem. In theory, of course, the limit comparison theorem is always going to work once you have that. We could have, in fact, done the limit comparison theorem on the guys that we, well, with the ones that had trig functions in them, then that's going to be still kind of hard to do limit comparison theorem with. You'd still want to replace them. But with the, like this guy, we could have done the limit comparison theorem with 1 over x squared. It would have still worked out. And we can do limit comparison theorem with this guy because I changed things in such a way that I'm not sure who's bigger or smaller. And that's what the limit comparison theorem, that's a nice thing to do. All right. So hopefully that's clear. Hopefully at least we start to appreciate that we do need to go review some stuff from Calc 1. Need to remember about limits, need to remember about how to shift functions, how to manipulate functions, and how the functions are going to behave under said manipulations. Remember simple things like you can make a denominator, you can make an overall fraction bigger by making the denominator smaller or making the numerator bigger. By the way, there is going to come another point in this semester where everything I'm mentioning now that I said you need to know from your limits, you're going to need it again for other topics. So everything I'm mentioning in today's lesson is actually very important to remember for the future. There's going to come a point where we're going to be using these same ideas again. We're going to talk about things called series eventually, and the series, they count off to infinity, at least the ones that we're going to look at. And so all the things about, you know, counting off to infinity and making comparisons, it's going to be very important. So everything I mentioned here is actually going to be very important for the future, just so you know. All right. And that is the idea of an improper integral. So we looked up at how to do all sorts of integrals in this course. And at this point, we just discovered how would we compute an integral that doesn't obey the fundamental theorem of calculus. The function is either not continuous or the endpoints go off to infinity. And another topic, which technically this was in the section before this, we're going to learn about numerical integration, because there are times when we have an integral that's very important, like let's say this one, where it's not improper, but so I can't really use limits or anything like that we use for improper integrals. But at the same time, it's really hard to compute. And at the same time, I would actually like to know an answer for it. I'd like to know a specific answer, right? There are times when we have integrals that are hard to compute, as you saw in this section. They're hard to compute, but at the same time, I can just determine what's going on using a comparison. So I can tell you that it converges or diverges, but I can't really say to what. So in the next section that we're going to really cover, I want to discuss that scenario. We're going to do what's called numerical integration, which is basically, I'm going to teach you some tricks that your calculator or a computer algebra system would use to compute a definite integral, right? Now, when you're a computer, it's much nicer, but I'm going to show you what the computer is thinking about when it's doing certain things. And the computer is going to do things millions and hundreds of thousands of times, but I'll just ask you guys to do it 3 or 4 times just to kind of get an idea. So that's actually coming up. But I don't really want to start that now, because then I'm not going to finish. So instead, what I wanted to do is take like 10 more minutes maybe and just kind of end this class with a little bit of fun. So hopefully you guys are perked up, ready for an activity. I want to do an activity with you guys that I did with my class in the spring. And it's probably something I should have done right after. Yeah, it's going to be fun. Not fun in quotes, actually fun.
I wonder what the fun is.
Yeah, okay, so I'm gonna tell you. So this is really something that we should have done at the end of integration. So integration, as like you guys have been asking me about questions from homework and things of that sort. So to try to figure out just integration techniques. How do I apply an integration technique? When do I apply it? How do I get good at integration? So I gave you guys the steps that you want to go through. And how do you go about actually getting good at the steps? Right? Is it an integration bee? Almost.
Before you get to the fun activity, so according to the last problem, you said like I converges by limit comparison. I said it converges. Well, remember when I said it converges to 1? We got 1 greater than 0, positive real number. But does it really converge to 1? Because in that case,
no,
that's what I got.
This limit converges to 1. The original integral we don't know.
Original integral, well, that's what I got. I said it converges to 1 because the limit is 1, and that's why I said
yes, but the limit and the integral are different. They're not the same. This might not add up to 1. This can add up to something larger. The limit converges to 1. It just tells you that the integral converges. It doesn't tell you what the integral converges to. To figure out what the actual integral goes to, tomorrow's lesson is going to go into that. Anyway, all right, let's start. Let's go into the fun activity. So when I was a little Jhevon, one of the ways in which I learned to be good at integration, and this worked with several other things, is I'd often make a game out of it. And it's even better with competition. Like you can play games with a friend, right? And you can make whatever stakes you want. You can be like, okay, if I win, you buy lunch or whatever, right? So you can make a little fun out of it. Okay. So here's the thing. I don't want to get all, Sun Tzu out of war on you guys, but the battle is won in the mind, right? You go to sit for a test. Here's the situation you want to be in. You want to be in the situation where you can look at a test, you can see all the problems, and you will know what to do. Your mind, you've already done the test. The test is already dead as far as you're concerned. Now it's just for the formality of writing out the solutions, right? The battle has to be won before you even start fighting. You can understand, like you see the move like when Sherlock Holmes is like envisioning he's beating this guy up and he can plot play for play in his head. That's what I want you guys to be able to do with integrals. So how do you actually get to the point where you can do this? How do you get to the point where you can look at an integral and you can know, oh, this is what I would do. You do a partial fractions. This part here is going to be a trig sub. That part over there is going to that, right? You want to just do it. Practice, exactly. But practicing a lot of integrals, sometimes it's time consuming, sometimes it's boring and not very exciting. So what you want to do is after you did go through the homework, you do a few integrals by hand the long way, and you really start to learn the ropes, and you kind of feel comfortable, but you're not quite comfortable, then you can play a game like this. Okay? So this is going to be a way for you to practice integration in your mind, and you're only going to be taking a few seconds per integral, so you're going to be able to practice a lot of integrals. It's like you are going to be able to do hundreds of integrals in a few minutes. Like that's what we're kind of aiming for. You're going to get all that experience, like literally like the Matrix, right? You know, like how Neo in the Matrix, and he uploads all this data, right? If you can get to play games like this game and games like this, that's what it's going to be like for you. You're going to be like that kid who can take 10 minutes before an exam and literally practice 100 integrals, while someone else writing out the integrals by hand they took like 30 minutes to just do 2 problems. Okay, and here's how we're going to do it. Non-integration jeopardy. We're actually going to do the integral by practice. So, and it's going to be very hard to start off, but the more you play this game, the more you kind of engage with it, the more you kind of try to do this practice, the better your brain will get. And I'll tell you guys a little story about that maybe another time as well. But just trust me, if you trust the process and you actually do this, you will be amazed how good you are, right? So, all right, so that's what I'm going to do with you guys. So here on this page over here, I posted a bunch of integrations. I took a bunch of textbooks and I copied up all the integration review sections from those textbooks. So hopefully you're seeing this. Okay, so what we are going to do is, here's how it's going to go down. Hopefully you guys are ready. And it's hard to do this online. It's much better in person. So I don't know how this is going to work. Maybe you guys, instead of typing, you're going to have to use audio or something, because you're going to have just a few seconds to respond. But that's the fun of it. You have to respond in a few seconds. So here's how is it going to go? I'm going to scroll to this page. I'm going to pick a random integral, right? You guys have 5 seconds to respond with the strategy for killing that integral, right? So I'm going to point on a random integral, and you are going to tell me how you would attack that integral, right? You're just going to respond. However, here's the thing. You have to be specific. You can't just say, oh, I would do a substitution. No, you would have to say, I would do a substitution of u squared equals 1 plus x squared. Right? You'd have to be very specific. You'd have to know how specifically you would attack that integral. Oh, I would do partial fractions, and on the second part, there's going to be an arctangent. Or I would do a substitution of u equals x squared, and that's going to turn into something where I would do integration by parts. Your goal is to be able to say a statement like that, but you need to say it within 5 seconds. If you don't do it within 5 seconds, you die, right? And if I was in person, I don't know, I'd slap you on your hand, or you'd pay him for lunch, or you get $1 for every integral you get right, and you pay me $1 for every one you get wrong. You can make it fun. You can make it interesting. Okay? All right. So that's what we're going to do. You guys ready? Okay, so if you're not ready, that's even better. Let's go. This one, strategy. Okay, you're dead. Too much time. Okay, this one, go.
U substitution. LN.
Substitution, what would you substitute? U equals LNT.
U equals
Good.
LNT.
All right, you guys got that. This one, go.
Trig substitution.
U sub.
A little bit more specific. Trig substitution, yes. I consider that half the answer. How do you do the trig substitution? What is it going to be?
X equals secant.
No, like you can't say that right away. So what a full answer like this would look like is you would have to say something like, I would complete the square, then do a trig substitution, right? It's going to be hard for you to tell it right away what it is. But if you could tell me whether it's a secant or not, that's going to be great. So it's going to be x minus 2 equals something, right? It's going to be x minus 2 equals like a secant, 2 secant something. So you guys got that. This one.
U
Okay,
substitution.
guys are dead.
U sub.
No, not U. U substitution would not work. You're still dead. This one right below it. Not specific enough, Dawa. Okay, U equals arctangent is how you would do that. So I'll give you that, even though you kind of took a while to follow up. Okay, what about this one?
U substitution.
What would you substitute? No, that won't get it. What, the one right above it?
Yeah, this would be U substitution, and then U.
That one's going to be U substitution. That one's clear.
one. Yeah, 1 plus.
What
X
about
squared.
this one? This one is the problem because of the 1 plus. What about this one? 95. Okay, you guys are dead.
U substitution.
You're
U
dead.
substitution.
89.
U equals e to the t.
Okay, then what's going to happen?
Then dt equals et, and then u squared equals e to t.
Okay,
I got-
and what's going to happen?
And
How would you
then-
do that new integral?
And then I go for
Oh, partial fractions.
Partial fractions. So a full answer to this would be someone to say, I would do a substitution, u equals e to the t. It will then put me in a situation where I would do partial fractions. I do expect you to be able to see that in 5 seconds. You know what I'm saying? Like when you're actually writing down the solution to the integral it's already dead. Like his destiny has happened, right? The moment he decided to show up on your test, he's gone, right? But you need to be able to see his destiny, right? All right, what about this one?
A U substitution.
Integration by parts.
Wait.
Tabular method.
Yeah, U
What-
substitution.
what
U
would the
equals,
parts be?
Wait. Never mind.
Wait. Yeah, u equals x to the 5, and v equals e to the negative X.
You realize that x is cubed, right?
So you can't do that, right?
So you can't do that because you don't know how to integrate the x cubed. It turns out that e to the minus x cubed has no antiderivative. It turns out that both of you are correct. It's a two-technique problem. You would first do a substitution, u equals minus x cubed. That would lead you to a situation where you do integration by parts.
Thanks.
Because when you take the du, you're going to get an x squared, then you're going to be left over with an x cubed. You're going to change and you can do integration by parts after. What about this one?
You first simplify. So
How?
you factor out a radical x from the bottom,
Okay, and then what?
and then you get 1 over radical x times
Okay.
1 plus x.
How do you deal
And
with that?
then you would substitute u equals 1 plus x.
No,
Partial
you would
fraction?
substitute u equals radical x. Almost, half credit. U equals radical x is the proper substitution there. Then this would become 1 over 1 plus u squared. And that's an arctangent. This is actually it's going to be something arctangent of radical x. This one? You guys have died too long. And that one isn't even a bad one. This one.
U equals x.
No, you simplify.
It's simplified. It's a step 2.
Damn it.
No substitution necessary. Just divide. Come on.
Yeah.
You guys are thinking too hard. This one.
It's u sub, right?
What would you substitute?
U equals x squared
No.
minus 9.
Wait.
Wait, what?
What was the
about
answer?
this? U squared equals x squared minus 9.
Oh man.
What is this one?
This is
double
Trig identity.
angle.
You
Yeah,
guys
double
are
angle.
That's not double angle formula. No. You'd save a secant squared, change the other secant squared to tangents, then do u equals tangent, right? So what about this one?
Integration by parts.
What are the parts?
U equals x and a v
Okay.
equals.
What about this one?
X.
Dx and then
Tell me the answer to this.
Oh,
5 seconds. Okay, you guys are dead. That's just a fancy way of writing x cubed, right? Let's undo. We got this wrong.
Oh yeah, it turns into x squared.
Right, it turns to an x
Damn it.
squared, and then you just integrate x cubed over 3 is the answer. What about this one? Sine of 1 over x squared. Maybe tell me the answer. What's the answer? You guys died. Okay, that's a substitution. U equals 1 over x. Your du is going to be minus 1 over x squared. The integral is going to be cosine of 1 over x. Because your du is going to be the minus dx and blah, blah, blah. Okay. So, yeah. So that is, that's the game. Essentially what you're going to do, you want to get really good at something, you go through homework, you painstakingly go through a few problems, right? Because you cannot, you can't at the end of the day escape hard work. It's just not going to happen. Like if some student comes and tries to do what we just did without actually going slowly through the process, it's not going to benefit them as much. So you go slowly through a process, you have to struggle with some integrals. And then you kind of try to get methods going in your head. And then you test yourself with this. You go like lightning round. You're giving yourself 5 seconds, 10 seconds. You know, you're like Rock Lee. If I don't get this in 5 seconds, I will do the next one in 3 seconds, right? And you're just like, you just go through. And you'll be surprised. Eventually your brain will get so good at doing this. Like I didn't plan what I was gonna ask you guys ahead of time. And I'm looking at this and I could see what the answer was already, right? And this is something that you guys will be able to do. And it actually, surprisingly, doesn't take that long. A week or two of intense practice and you guys will be better than at integration than I am, honestly. Like you can get there, right? So you get to a point, you should be able to get to a point where you can look at something, you can know what the answer is, and it's just a matter of formality and writing it up. Okay? So that's gonna be the goal. And maybe next time I'll tell you guys a story about that, where I actually used this situation back when I was a young Jhevon and some of the results. But we are going to end right there. Yes, the narrative reference. But that is it. That is the end of today's class. We went through improper integrals and some integration techniques. Tomorrow we are going to do, you can do this weekly, but you guys have to do it on your own. I can't spend time doing this all the time. So tomorrow we're going to look at numerical integration, and then we're going to move on to, afterwards, I believe, sequences, but that's maybe the following class. So we'll start right there. Yes, the video for yesterday's class probably just went up while we were in this class, and I'll post this video with the notes there as well. Yeah, sequences and series is going to be great. It's going to be fun. For now, that is it. I will see you guys in the next one. Have a lot of fun, do a lot of practice, finish your homework, and I will see you guys around. Ciao.